This is required practical number 4. It's really Ohm's law. In it, you need to use a circuit diagram to construct appropriate circuits to investigate the IV characteristics of a variety of circuit elements, including a filament lamp, a diode, and a resistor at constant temperature. In plain English, this means you look at what happens to the current when you change the potential difference or voltage across the 3 different components. What we find out is that all devices have a property called resistance. This is a measure of how difficult it is for the current to get through and is measured in ohms. The more ohms, the more difficult it is for the current to go through. The circuit setup is the same for all 3 elements. In this case, we're going to be looking at a resistor which keeps a constant temperature. You need a power pack like this one. Notice we're going to be using direct current or DC. The electrons will come out the negative terminal, shown by the black wire and the black terminal, and travel through a gold-coloured resistor. The current is measured using an ammeter which is placed in series. This is a device with a big letter A on it, and it will measure the current in amps. Ammeters are always placed in series with components. They have a very, very small resistance. We only need one ammeter because it is a series circuit and the current will be the same throughout it. We record the potential difference with a voltmeter. This is shown by the device with a big V. This is placed in parallel with the device that we're measuring, in this case the resistor. Voltmeters have a very high resistance, millions of ohms in fact. Because it has such a high resistance and it is placed in parallel, it has very little effect on the current, in fact not one that we can measure easily. Some students incorrectly use the dial on the power supply as a measure of the potential difference. This should be avoided. It is a rough guide at best. In many schools, the dial is in fact pointing at the wrong numbers due to the over-enthusiastic nature of some students. Start with the voltage at the lowest possible setting, for safety reasons, then turn it on. Turn the dial till you start getting your first readings and gradually collect your set of results by increasing the voltage and measuring the current. The more results you collect, the easier it will be to see a reliable pattern. In this case, we will take 6. We have the option of taking more if our line graph does not show a clear pattern, or if it's just too scattered or there's anomalous results. Quickly make note of the values coming up and put them in a table with the correct headings and units. When writing the table, make sure you have headings and units. Also make sure they have a consistent number of significant figures. In this case, it's to 2 decimal points. The results are plotted on the graph, and you can see there a clear relationship. There's no need to take any more results. All the plots are close to the line of best fit, and there is a clear pattern. Whenever you comment on any graph, stick to these basic rules. It works for all exam questions. First of all, comment on the general trend. As X increases, what happens to Y? Then comment on any changes of gradients. In this case, there is no change of gradient. Also give read-offs to prove your point. In this case, there is no change of gradient, so we're going to have to add a bit more information to try to collect as many points as possible. So here we go. This is the perfect answer. As the potential difference increases, so does the current. Indeed, the current is directly proportional to the potential difference because the line is a straight line going through 0, 0. For example, when the potential difference was 5 volts, the current was 0.22 amps. And when we doubled the potential difference to make it 10 volts, the current also doubled and became 0.44 amps.